SwayamPrabha. Digital India. Educated India.
Hello and welcome to lecture 40. We are discussing design of low speed axial flow compressor. In last lecture we were discussing about design of low speed compressor for given data using free vortex concept. So in today's lecture we will be discussing using the fundamental design approach. So what all we have discussed in earlier class, our calculation, that's what will be starting with the mean diameter. So all parameters we are calculating at the mid station. So once fundamentally we learn, we are doing our calculation at the mid station, say especially for low speed axial flow compressor, we are considering our mid station as 50% of the span. Okay. So based on our understanding, we will be doing all our parametric calculation, and after that we will be applying our design approach. So let's see what all we have done in sense of say mid span calculation. So we will not be discussing again like what all we have done at mid span calculation. So if you recall, when we were discussing say design using free vortex concept, we have made this mid section design calculation. So here if you look at for this fundamental approach also at mid station, we are considering our say pressurized delta P0 at the mid station to be say 1000 Pascal, and this is what is all data what we have considered with. Now this approach, if you recall, when we were discussing different design approaches, that time we have discussed there is a flexibility in sense of varying my delta P0. So my delta P0 I can distribute in a way like if you look at here, this is what is say hub loaded configuration, say this is what is say mid loaded configuration, and third if you look at this is what is representing tip loaded configuration. So here in this case at mid station we will be doing all our calculation and we will be assuming our delta P0 at hub and we will be assuming our delta P0 at the tip station. And then after this delta P0 we will be dividing in 11 stations, say 5 station below my mid span and 5 station above my mid span, such a way that will be giving me uniform distribution of what all parameter we are targeting. Mainly when we are saying our parameters, we are more interested in sense of blade angles, because if we will be having say uneven variation of blade angle, that may lead to make the blade to be zigzag. So we will see what all we need to take care of when we are doing the design using this fundamental approach. Okay, so this is what is all we need to start with. So at mid station we already have done our design. So let's move here. In this case, let's assume say at hub we will be considering our pressure to be 800 Pascal and at the tip we are considering our pressure to be 1200 Pascal, and at mid station we have done calculation for 1000 Pascal. Okay. So at hub and tip we need to do our calculation. So here if you look at, let's start with the calculation at the hub. So this design approach, that's what is different from what we have discussed for free vortex design. So here what all we need to do is we need to do our calculation at the hub station in sense of flow angles. Okay. So suppose if I consider this is what will be my velocity triangle at the hub. You can say my U hub. So U hub we can calculate based on say pi dn by 60. Since my hub diameter, that's what is say 0.2, we can do that calculation. Same way at hub we can do our calculation for beta 1. So this beta 1 at the hub, that's what is given by UH by CA. Since our peripheral speed at the hub it is known, we are assuming our axial velocity to be constant throughout my span. That's the reason this is what all we have already calculated with. It is say 36.69 meter per second, and that's what will be giving me my beta 1 as say 34.41 at the hub. Okay. Now what is my next required parameter? That's what is say my beta 2. So here in this case, when we are looking for the calculation for beta 2, we need to compare our aerodynamic work and thermodynamic work the way in which we have done calculation for the mid station. So in order to do that calculation, what we have assumed? So we have assumed our delta P0 at hub to be 800 Pascal. So if this is what is your case, you can calculate my P0 at the hub. That's what is say P01 plus delta P0H. That's what is coming say 102.125 Pascal, kilopascal. Okay. So based on this calculation, we can do calculation for the pressure ratio at the hub. That's what is coming 1.0079. Okay. So this approach, that's what is somewhat different compared to what all we have discussed in earlier case. Now once this is what is known to me, we can calculate our delta T0 at the hub based on our fundamental equation. Since our efficiency it is given 80%, so we can write down this number. Say we are assuming our T01 at the hub to be 298 only. So that's what is giving my delta T0 at the hub as a 0.83. Okay. Now once this is what is known to us, then we can do our calculation for the blade angle, or we can say relative flow angle at the exit of our rotor. So what we can do, we can compare our thermodynamic work and aerodynamic work. Our work done factor, that's what we have assumed to be 0.98. If we are putting this number, that's what is giving me my beta 2 at the hub to be minus 13.87. So be careful when we are doing our calculation. Accordingly, you need to modify your velocity triangle. Okay. So here if you look at, this is what is my velocity triangle at the entry, and this is what will be my velocity triangle at the exit of my rotor. So here you can see this is what is representing my beta 2 at the hub to be minus 13.87. Okay. Now what we know, we can calculate our delta beta based on what parameters, say beta 1 and beta 2, that's what is known to us. That's what is giving me my delta beta at the hub to be 48.28 degree. Okay. Now same way we have done calculation for the specific energy, we can write down, say that's what is given by Cp delta T0. We can do our calculation. It says this is what is coming 842.1 joule per kg. We can calculate what will be our total work requirement at the hub station. Here in this case, we need to be really careful of what parameters we are calculating, because my delta T0 at the hub, it is different. My delta T0 at the mid, it is different. My delta T0 at the tip, that's what is different. And that's the reason why my total work that also is varying along my radius, or we can say that's what is varying along my span. So basically when we are calculating this total work done at different station, we will be averaging out that, and that's what will be giving us what power, that's what is required. We will see what is the difference in sense of power when you are using your free vortex concept and when you are using your fundamental concept. But this is what is a way in which we are calculating our total work done. Now once we have calculated that part, we can do our calculation about say what will be my say world velocity component. So what we know from our velocity triangle, just write down this carefully. It says this is what we are writing in sense of say different formulation. That's what is giving me my CW2, that's what is equal to 34.19 meter per second. Okay. Now once we have calculated what is our CW2, we can calculate what our alpha 2 is, and this is what is giving me 42.98 degree. Since my beta 1 and beta 2, that's what is known to me, my Ca by U hub, that is also known to me, we can calculate what will be our degree of reaction at the hub. And if you are putting this number, it says our degree of reaction, that's what is coming 0.32. So we can understand degree of reaction at the hub, it is coming 0.32. That's what is a reasonable number in sense. Okay. So this is what we can say, fine. Okay. Now careful here, suppose say my degree of reaction at the hub is coming negative, then we are having problem. What we need to do? We need to do our recalculation, that's what will be starting from what P0, what we have assumed, delta P0. You need to adjust that number in such a way that my degree of reaction at the hub, that will be coming more than 0 or that will be coming positive number. Remember this part. Okay. So what assumptions we have made, 800 Pascal, you can assume 500 also, even you can assume 400, but you need to be very careful when you are doing your calculation, your degree of reaction, that's what is a first cut check. Okay, it should not come negative, it should not come 0. Okay. Now once this degree of reaction, that's what is known to us, we can do same calculation in sense of our de Holler's number or relative velocity ratio. So if we are putting this in the formulation, so V1H, that's what we can write down in sense of cost component, and it says this is what is coming 44.47 meter per second. Same way here in this case we can do our calculation at the exit. So this V2H, that's what is coming in sense of Ca by cos beta, and that's what is coming to be say 37.8. Now we are having this number, we can understand we are looking for say diffusion. So our de Holler's number, that should come more than 0.72, and here if you look at, this is what is coming 0.85. So we can say we are in a safe range. Okay. Suppose say this is also not coming, then again you need to go with the iteration for assuming our delta P0. Okay, so this is what is little iterative. So in sense of making this numerical simple for understanding with more complexity, we have assumed this number. Okay. Now once we have done our calculation, our next parameter we are targeting, that's what is my diffusion factor, and in order to do the calculation for the diffusion factor, we need to calculate what will be the solidity. Okay. Now for calculation of solidity, we need to check with pitch and chord. So it says pitch, we can say that's what is pi d by z. My hub diameter, that's what is known to me, very careful. We are doing our calculation at the hub station. That's the reason, do not forget you need to put hub diameter. Now in order to avoid the confusion at this moment, what numbers we have assumed for free vortex, same number we are considering. So for this case, our number of rotor blades we are assuming to be 15. So it is possible for us to do one-to-one comparison. No one is stopping you to change this number of blades again. Okay. So here we are considering this to be say 15. So if we are putting this as a number, we can calculate our pitch, and that's what is coming 0.0419 meter. And my solidity, that's what is coming 2.387. Okay. So, if this is what is known to us at hub station, we can do calculation for the diffusion factor. And as we have discussed, when we are talking about say rotor, for diffusion factor calculation, we are considering these angles to be beta 1 and beta 2. Very careful what all we are writing, that's what is at the hub station. And it says at the hub, we are getting our diffusion factor to be 0.31. So, we can say this is also in a reasonable range. We can say this is what is okay with. So, we have done our calculation for degree of reaction. We have checked with relative velocity ratio. We have checked with the diffusion factor. So, what number 800 Pascal pressure what we have assumed at the hub, it seems to be okay with us. Okay. Now, once we have done the calculation for the hub, we need to check at the tip also. So, for the calculation at the tip, this is what we can say, my alpha 1 at the tip, that's what is 0. We can do our calculation for the peripheral speed at the tip, that's what is given by pi d and by 60. My tip diameter at this moment we are considering 0.4 meter. So, that's what is giving my u tip to be 50.26 meter per second. Okay. And we can calculate what will be our beta 1 at the tip based on the velocity triangle. At beta 1 at the tip, that's what is coming 53.87 degree. Okay. In line to what we have done calculation for the hub station, same way we can go with the calculation at the tip station. So, what we will be doing? We have our delta P0 at the tip, we have assumed at this moment to be say 1200 Pascal. Okay. So, if we are putting that, it says we can calculate our outlet pressure at the tip. Be careful, P01 at the tip, that's what is say 101325 Pascal, and this is what we are assuming 1200 Pascal. So, that's what will be giving us say our pressure ratio to be 1.011. Okay. From our fundamental understanding, we can do our calculation for the temperature rise. So, here if we are putting this number, it says our temperature rise or total temperature rise, that's what is coming to be 1.25 Kelvin. Okay. Now, once we know what is our delta T0, that's what will be helping us for the calculation of our other parameter. What parameter? We want to calculate what is our wall component, or what will be my blade angle, okay, or what will be my relative blade angle. So, here in this case, if you look at, we can do balancing between aerodynamic work and the thermodynamic work, and if we are doing our calculation, that's what is giving me my beta 2 to be 33.9 degree. Okay. So, this is what is giving me 33.9 degree. Once this is what is known to us, we know what is our beta 1 at the tip, we know what is our beta 2 at the tip. So, we can calculate delta beta at the tip, that's what is coming 19.97 degree. Okay. And same way we can do our calculation, this is what is for our understanding. Intentionally we have kept this, it says if I am calculating my total power, that's what is coming say 5.045 kilowatt. So, you can understand we have our design, that's what is tip loaded design. My hub is less loaded, my mid section is mid loaded, and the tip it is highly loaded. Okay, and that's what is giving my power requirement for that station, that's what is coming to be larger. Okay. Now, as we have discussed for our hub, we can do our calculation for the tip station, and we can calculate what will be our CW2. Okay. So, based on our fundamental equation and velocity triangle, we can calculate our CW2 at the tip, that's what is coming 25.61 meter per second. Okay. Now, once this CW2, that's what is known to us, we can calculate what will be our alpha 2, and this alpha 2, that's what is coming 34.91 degree. Okay. Now, once this is what is known to us, we can do our calculation for degree of reaction. because my beta 1 at the tip is known, my beta 2 at the tip is known, my CA and U tip, they are known to be. So we can do our calculation for degree of reaction, and that's what is coming 0.74. Okay, so we can say now this is also coming in a reasonable range. Okay, and reasonable in the sense at the tip we will never be having this degree of reaction to be coming negative or say 0. So that's okay. Okay. Now we will be checking with what is happening with our relative velocity ratio. So based on our velocity triangle at the entry and velocity triangle at the exit of our rotor, we can do our cos correlation. It says my V1, that's what is coming to be 62.23 meter per second, and same way at the exit we can calculate our relative velocity, that's what is coming 44.2 meter per second, and it says my relative velocity ratio, that's what is coming 0.71. So this is also in the range of what we can say 0.72. So we are not bothering at this moment in sense of this number also. Okay. Now we have done all this calculation. Next parameter we need to check, that's what is with the diffusion factor. So for diffusion factor calculation, as we have discussed earlier, we are looking for the calculation of the solidity. Be careful here, when we are calculating our pitch, we need to consider our tip diameter and number of blade, that's what is say 15. If you are putting that number, it says my pitch, that's what is coming 0.0838 meter. Okay, you can understand my pitch at the tip, that's what is coming to be larger. My pitch at the hub, that's what is coming to be lower, because that's what is a function of my radius. Okay, my chord, that's what we have assumed to be constant, so we can say solidity, that's what is coming as 1.19 at the tip station. Now once this is what is known to us, we can do our calculation for the diffusion factor for rotor at the tip station, and that's what is coming 0.4619. So we can say this is also coming in a reasonable range. 0.46, it's okay. Okay, so we have done our calculation at hub station, we have done our calculation at the tip station, and we have verified our required parameter in sense of degree of reaction, relative velocity ratio and diffusion factor. And we have calculated all our flow angles as well as our say velocity components. Now let's come to what all we have done. So as we have discussed for our fundamental understanding, again when we are using this fundamental method, for that also it is preferred we will be doing our calculation using Excel sheet program. Okay, so this is what is my mid station calculation. Okay, so that's what will be remaining same. Okay, that's what we have done our calculation for say our free vortex design. Same logic, that's what is applicable here. There is nothing different in sense of say these numbers. Okay, here in this case where the change, that's what is coming, that's what is coming here. Now all our calculation, that's what is based on delta P0. So here for hub we have assumed that to be 800 Pascal, and for the tip we have assumed that to be 1200 Pascal. And if you recall, when we have done our calculation for free vortex at mid station, we have done calculation for CW2 into R2 at mid station, that's what was giving some constant, and from that we have done our calculation for say our tangential velocity component or wall component. Here in this case we are doing our calculation based on delta P0. So here if you look at based on this delta P0 we are doing our calculation for CW2, we are doing our calculation for beta 2 and all those numbers. Okay, so this is what is the difference, and that's the reason why intentionally we have done our calculation at the hub station and at the tip station, so that you will get clarity how exactly these numbers are coming. There is nothing magic in doing this calculation. Okay, so be careful. You just make your Excel sheet program. That's what will be ready for this fundamental method also. Okay, now here in this case, if you look at, this is what is giving me my 1000 Pascal. So, if you are taking your average, that's what is giving me 1000 Pascal. This is what is my requirement. Okay. Now here if you look at my delta beta, that's what is coming 48.28. You can say this number is coming slightly on the higher side. We are looking for our delta beta to be in the range of 45. And this is what is coming slightly on higher side. So, you can understand we need to do something for changing this number. Let's see what to do with. Here if you look at, this is what is giving me idea about the degree of reaction. We have no issue with degree of reaction at the hub. That's what is coming to be positive. So, it's okay. We are considering our relative velocity ratio. That's what is it is changing from 0.85 to 0.71. So, this 0.71, that's what we'll say, okay, we need to do something there in order to modify this number. Okay. Now, next, that's what is coming in sense of my diffusion factor. So, here if you look at my diffusion factor, that's what is coming 0.31 at my hub and 0.46 at tip. Okay. Now, as I told, we have so much of flexibility by using this Excel sheet program. Suppose you want to modify your diffusion factor. What change you will be doing? You will be changing your number of blades. Okay, just change that number of blades. That's what will be changing all your calculation for diffusion factor. That's what will be giving the change in your camber angle and all those parameters. Because your pitch, that's what is changing. Okay, so your camber angle will be changing, your deviation angle will be changing, your stagger angle will be changing. They all are interrelated parameters. So that's what is the flexibility. So you can say here I can play with changing the number of blades. You say I need to go with some higher loading. I'm looking for higher tip loading compared to 0.46. I want to go with 0.5. Yes, you can play with these numbers. You can change your chord, you can change your number of blades. Okay, so that's what is the flexibility what we are getting when you are using this Excel sheet program. So that's the reason why I insist all the time, because when you are writing your code, for writing of code all the time we will be having different kind of feeling. Okay, and may not be calculating, will not be having the feeling of how my angles, how my parameter, that's what is changing at the hub, how my parameter, that's what is changing at tip. So this is what is, will give you feeling of exact view of how the variation, that's what is happening. Okay. Now let me discuss something different. Here in this case, as we have discussed, we are having our delta beta, that's what is coming to be large. Okay. So in order to address this kind of issue, just look at here this delta P0, that's what we have modified. Now let me put one point here. Okay. Now what we are expecting is our pressure rise, what we are expecting, that's what is 1000 Pascal. This all designs what we are doing, we are not knowing what kind of loss that what will be happening. This loss majorly is because of the tip clearance what we are having. Are we going in sense of 1 mm, 2 mm or 3 mm clearance, or be in sense of percentage of height? So, we need to take care at the initial stage only, so that later it will not create the trouble for us. So, in spite of having 1000 Pascal, let me consider slightly on the higher number. There is nothing wrong in doing this thing. Even for free vortex, at mid station you can take that number. There is nothing wrong in that. Okay, because we are not having idea what will be the losses and how much pressure loss that will be happening because of my tip clearance, because here we are not having any consideration for the tip clearance. Okay, so what we have done here in this case, you can say at hub we are having our say delta P0 is 699. At mid station also we have changed. That's what is the flexibility. That's what I was telling you. Say here in this case you play with this number and just check with what all changes. That's what is happening. Okay, so here at mid station we have considered that to be say 1070, and you can say at the tip we have considered that to be 1500 Pascal. Okay, now what will happen because of that? Just look at this delta beta here. For our earlier loading case, it was coming 48.28. That's what we have reduced to 41.80. Okay, where it is reflecting, you can say that's what is reflecting with our degree of reaction. So you can say my degree of reaction, that's what has increased near the hub region. Now what is happening at the tip region? It says my degree of reaction, that's what is decreased by say 0.682. Earlier it was say 0.74. Okay. Now when we are comparing our relative velocity, it says my relative velocity I have moderately compiled here at the hub, but near the tip region that's what is coming to be slightly on the lower side. We prefer to have 0.72, but this is what is coming around 0.66. It's designer's choice. You can play with the numbers. Here you can modify that part. And if we compare our diffusion factor, just look at the hub we are having our diffusion factor to be 0.30, and at the tip we are having diffusion factor to be 0.55. So you can say we have increased our diffusion factor near the tip region by changing our loading. Okay, so accordingly if you compare your angles, it clearly gives we are able to maintain our camber angle within certain range, because my blade twist, what we say in sense of delta beta, that's what is very important. Okay, and if you recall, for free vortex design we have realized our delta beta, that's what is coming to be say higher near the hub region, and we have no control for that. It is by default it will come because my diameter is smaller, maybe my rotational speed, that's what is smaller, so my u will be smaller. Now here in this case, when we are opting for this design concept, that's what is in our own hand. We can control in sense of degree of reaction, we can control what blade turning angle we are looking for. And that's the reason why this is what is one of the fundamental, I say, this is what is a fundamental method, and that's what is most preferred. Most of the design, what all we have done up till now, that's what is based on our fundamental approach. And there is nothing wrong, all what stages we have designed, what all rotors we have designed, using this concept, they are safely running without any problem. Okay, so we can realize now this is also one of the approach for the design. So later part in sense of how we will be dividing, that's what is very important, that's what we will be discussing in the next session. But you just realize one thing, say when we are comparing our design aspect for free vortex and the fundamental method, we are having more flexibility when we are approaching or when we are using our fundamental design approach. Okay, and we must realize what are the benefits of using this Excel sheet program, and we will soon be realized and we will be getting matured with using these Excel sheets only, as in when we will be doing our design, we will be having Excel sheet program with us. Okay, so now in next lecture we will be discussing, here we have discussed about what will be my delta P0 at hub, what will be my delta P0 at the tip. Now at 11 stations we need to distribute that delta P0 in a systematic way. Then only we will be getting our smooth curve for the blade, otherwise it will be creating trouble. Okay, then we will be discussing how do we do our design for the stator, and we will be finalizing the stage design. Then we will try to understand what all changes we are bringing by incorporating free vortex method as well as this fundamental method. Thank you very much. I do prefer you just go with doing the Excel sheet program, and at the same time you just try to make the code for making of blades. Thank you once again.